Good evening, everybody. I trust you're hearing me. Um, this is Thomas Clarke. I am the operations officer at the Harry Bayley Observatory. Not had much to do during the COVID lockdown, but hopefully, things will change in the near future. I often do, from time to time, I do a presentation on Friday nights when we did have presentations on Friday nights on the sort of the scale of the universe. And the challenge is that the numbers are so large that it really becomes meaningless. So about a year ago, I had this bright idea of let's let's look at the solar system under the assumption that the Earth is the size of a marble. So we're bringing the Earth down to the size of a marble, which is a marble from my research. These are not the big marbles, these small glass marbles that we used to pitch when I was a boy, is about a half an inch, 13 millimeters to be precise. So we're scaling the Earth down from a diameter of 12,000, some nearly 13,000 kilometers in diameter, down to 13 millimeters. And then we're going to look at how the sun and the planets in the solar system scale, and we're going to apply that scale to known areas in Barbados. So if we scale the Earth down to 13 millimeters, the size of a marble, the sun will then have a diameter of 1.4 meters, which is like a little over 5 feet. Okay, so the Earth is the size of a marble, and the sun is a little over 5 feet, 1.4 meters. let's look at some of the distances involved. So what I did is I decided, for whatever reason, my center of the solar system is the control booth on the swing bridge in Bridgetown. You know, the swing bridge was updated, and there's a control booth in the middle of the bridge that controls the opening and closing of that bridge. So if the sun, with its 1.4 meter diameter, was placed where that control booth is, let us look at the planets in the solar system, how they would relate to that location. Mercury, which is the smallest planet in the solar system, at this scale would have a diameter of 5 millimeters, a little less than, I'll call it approximately a third the diameter of the Earth. And at that scale, the orbit would be 59 meters from the sun. Now, what does that look like? If we're at the swing bridge location, 59 meters is basically it's basically where the fountain is. I didn't do it on this Google Maps, but it's basically, if you look from the control booth, it would be pretty well where the fountain is across the road. That would be where Mercury is. Venus would be would be about twice that distance. And that would be sort of across the road, sort of close to the far end of Chefet, just across the road. So if you went across the road and went past Chefet to the end of it, there's a shop there or something that sells sunglasses and so on. I don't remember the name of it, but that's where Venus would be. Where would the Earth be? Well, the Earth at this scale, we didn't write. The Earth at this scale would be 153 meters away from that control booth for the sun. And that is, the Earth would be right at the corner where you turn to go to First Caribbean Bank. So if you walked along the wharf road from the control booth, and you got to the road leading up to First Caribbean, that's where the Earth would be. The next planet out from the Earth is Mars. Sorry. Let's just backtrack. Let's talk about the Moon. Now, at this scale, the Moon is 4 millimeters. Remember, the Earth is 13 millimeters. The Moon is 4. A good idea of the size of the Moon in realistic terms is the Moon is about the same as the width of Australia. So that's a pretty good way of looking at it. But in our scale, it's 4 millimeters, and it would be 0.4 of a meter away from the Earth. So the Earth is sitting on our solar system scale. It's sitting at the corner, going to First Caribbean, and 0.4 of a meter around it is where the Moon would be. The orbit of the Moon would be happening. Okay, the next planet outside of the Earth is Mars. Size-wise, Mars is 7 millimeters. Notice that Venus, by the way, I should have said, Mercury is 5 millimeters, a little bit bigger than our Moon. Venus is 12, almost the size of the Earth. And Mars is 7 millimeters. So Mars is like a little over half the size of the Earth. And its orbit would be 233 meters away. So on Google Earth, Mars would be right where the old immigration building used to be. So remember, the turning up to First Caribbean is where the Earth is. That's here. And then Mars is right outside where you would wait to go into the old immigration building. Right, the next planet outside of Mars is Jupiter. Jupiter being the largest planet in our solar system. With it's a little over 10 times the diameter of the Earth. With the Earth being 13 millimeters, Jupiter is 143. And it would be at 794 meters from our sun, which is the booth for the control of the bridge. And that puts Jupiter right outside the Bridgetown fisheries project. So if we're right where you turn in to go buy your fish, that's where Jupiter would be. All right, remembering that Mars was sort of where immigration was, and Jupiter is outside the fisheries complex. Saturn is the next planet outside of Jupiter. Saturn would be 119 millimeters on our scale, and it is at 1,459 meters away from our sun or booth. And that would place Saturn pretty close to the traffic lights, just by Kensington Oval. All right, so as you can see, Saturn is quite a bit further out, where Jupiter is. And the numbers that I'm using for these orbits are the average orbital distance. Many of these orbits are elliptical. So I'm assuming they're circular, and I'm using the average distance. All right. And Saturn would be 119 millimeters, where Jupiter is 143. So Jupiter is a little over 10 times the size of the Earth, and Saturn is a little bit smaller than that. This diameter does not include the rings. This is the diameter of the planet itself. Beyond Saturn, we have a planet Uranus, which is several times the size of the Earth, and it is at 2,928 meters, which would put Uranus just outside the psychiatric hospital. Okay, so you can see that some of the distances are starting to get quite a bit larger. Remember, the Earth is, from our starting point, the Earth is the corner going into CIBC in Bridgetown, and Uranus is way out by the psychiatric hospital. Beyond Uranus is Neptune. Neptune is slightly smaller than Uranus at 50 millimeters, and it is 4,591 meters out from the sun on average, and that will put Neptune out beyond the Esso roundabout below Cave Hill, sort of around turning where you would turn up to go to the Archives. All right, so we see, as you can see, we're getting right out into the outer reaches of the solar system. Pluto, which is now considered a dwarf planet. As you can see here, Pluto is really small. The Earth is 13 millimeters. The Moon is 4. Pluto is 2 millimeters in diameter and is a distance of 6,000 plus meters out, which would place Pluto sort of where Jordan's supermarket is in Pitts Village. So we've gone from the Earth being like here all the way out to Jordan's supermarket, which is the extent of the planetary component of the solar system. And I included the nearest star, Proxima Centauri, which the sun is 1.4 meters. Proxima Centauri is like a fourth the size of the sun, approximately at 388 millimeters on our scale, and its distance is 4.2 light years. Light travels at 300,000 kilometers per second, and a light year is 60 seconds in an hour, 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 and a quarter days in a year. So when you multiply all of that out, you get this number in kilometers. And on our scale, anybody care to hazard a guess where the nearest star to our sun, to Sol, Proxima Centauri, is on the map we have been using? Well, it is from Barbados. It would be right where the Suez Canal is. Okay, and that's the nearest star. Remember, the furthest out planet from with the sun at the center of that control booth on the careenage, the furthest planet out, the Earth is where the turning to first Caribbean is. The furthest planet out is was Pluto, which is where Jordan's supermarket is, and Proxima Centauri would be on that scale where the Suez Canal is. And that is the nearest star to us. Just for your information, because we're not really looking at the distances beyond the solar system, the Milky Way, which is our galaxy, is approximately 100,000 light years in diameter. The solar system, which we've been discussing, is some 26,000 light years from the galactic center. So we're sort of halfway out in the galaxy from the center. There are about 200 to 400 billion stars in our galaxy. And NASA in 2016, from what my research with them estimate, there's some 2 trillion galaxies in the universe. So we're only looking, I was only discussing our solar system. And, you know, as you can see that these distances are quite substantial. I mean, you know, the nearest star on this scale, where this is the Earth from the sun on our marble-sized Earth scale, the nearest star is literally halfway across the Earth. So, and there are 100 to 200 billion stars in our galaxy alone. And where we are is not a very dense region of stars. So as you start to see, the distances involved can be quite significant. I hope this helps you get an appreciation for how things are structured in the solar system, because often when you look in the magazines and you see pictures, everything is always squished together to fit on the page. But the reality is things are very, very spread out. And there's a lot of space between the masses, the planets in the solar system. There's a lot of space between the stars and the galaxy. And I hope this helps give you an appreciation for how things scale. Okay, I'm gonna hand back to David. And thank you very much for listening. Okay.
Yes, thank
back,
Jeez,
back to
Thomas,
you.
thanks. That was actually very insightful. I think, it's amazing when I think when you started to get to the likes of Jupiter and Saturn, then Uranus, and then you realize that the distances in between just kept getting further and further out. It is, it is really mind-boggling with the Earth. You said the Earth is scale is down to 13 millimeters in diameter, correct?
Size of a marble.
Size of a marble, and still we, even the solar system spans that's the order of kilometers.
Yeah, out to Jordan supermarket to Pluto, and the solar system goes beyond that. I mean, I have
The Oort cloud and what have you, yeah.
cloud on, yeah. I mean,
Mm-hmm.
there. I read that they consider the solar system can go halfway to Proxima Centauri. But I've seen some people say they think it's as big as light years out in terms of your cloud and objects in the outer solar system.
Yep. Yep. Interesting, yeah. It'd be interesting if the two probes, Voyagers 1 and 2, because they're still constantly sending back data. It's surprising data as well. It'd be interesting to see if, what new insights they can provide, because it'll be many years before we get probes out to that distance again,
Yes.
short of having some sort of new advanced form of propulsion. Those are the probes that we rely on to get any sort of perspective on what the solar system is like at those distances. Are there any questions for Thomas? No. Well, thanks again, Thomas. That was excellent.
You're
Much
welcome.
appreciated. Yes. All right. Okay. Matt, so are we ready?
Yeah.
Okay. All right. So I'm going to hand over to Max, and he'll start his presentation on black holes and supernovae. Give me 1 sec. Let me make you new folks. Alrighty, it's all yours.
Thank you, David. Let me see. Can you see my screen now?
Yes, you can.
Yes, again.
Okay. So good night, everyone. My name is Max Miller. I'm doing this brief presentation on supernovae and black holes. Supernovae and black holes, they tend to be an exotic topic when you go to the movies and you see what is depicted in the movies. You'll have people becoming superheroes by absorbing all the energy of an exploding supernova and using a black hole to get from one place in the universe to another, and so on. Of course, that's all fine in the movies, but in real life, I said I would just do a brief, simple presentation on what is known so far. Now, as I was going through this, I realized that there were a lot of things that, this would be a very in-depth discussion. So this is going to be quite high level. Now, a supernova is an event that occurs when a star basically explodes. They're quite rare. Approximately only 3 per century occur in our galaxy compared to a basic nova, which are estimated at approximately 30 to 60 per year. But because there are so many galaxies, billions of galaxies, astronomers somehow are able to observe supernova occurring in other galaxies. So they can observe at least several hundred per year. They're difficult to directly observe in our own galaxy because of galactic dust. And you know that I find that that is very interesting because when you think of the galaxy and you think of space, you always think of the vacuum of space, but there's enough dust flying around in space to hinder our view of seeing these supernovae in our own galaxy. Now, this this is something which I find difficult to grasp. A supernova is an extremely powerful event, creating an explosion brighter than the entire Milky Way. And we know that the Milky Way has in billions of stars. So the concept that one star exploding can create more light than all of those billions of stars put together is really quite intriguing. And I that goes down to the whole nuclear physics and why an atomic bomb is so much more powerful than a stick of dynamite and so on. But I found that to be quite an interesting fact. If our sun was to become a supernova, we would more than likely be instantly disintegrated. However, 4.5 billion years from now, approximately when our sun dies, it's not going to become a supernova for reasons that I will mention in a couple of moments. Now, for the purpose of this presentation, there are three basic types of supernova. There are more in reality, but I'm limiting it to three, and I'm using my own nomenclature. The type 1, which is caused by 2 stars. The first type of this is when a white dwarf star sucks material from an orbiting companion. So that would be like in a binary system. And the second type is when two white dwarfs collide. Now I call these types 1X and 1Y because in actual astronomy, there's a 1A and a 1B supernova, but that was getting so technical and into the different different spectra of light emitted and whether there's hydrogen in the star and so on, that I said instead of trying to reconcile my labels to the actual labels, I'll just make up my own labels for simplicity's sake. The second type of supernova is when a massive star dies of old age. And the third type of supernova is what they call a pair instability supernova. Sounds quite ominous. Now, when a white dwarf pulls material from the companion star, eventually enough material is sucked into this white dwarf to raise the core temperature enough to cause a runaway nuclear fusion, resulting in a supernova. So you've got your white dwarf there, the companion star is next to it, and this white dwarf, which has very strong gravity, is just sucking and sucking and sucking material, the companion star is also sending out solar wind and sending out material which is accumulating onto this white dwarf. And eventually, so much of it collects that it causes the process which causes the white dwarf to supernova, to explode. Now, you can get a kind of a similar sort of situation when two white dwarfs collide, The resulting shock wave creates a supernova. And this type of supernova is officially called type 1A supernova. Right? Now, the interesting thing about type 1A supernovas is that supernovae, sorry, is that they are actually kind of common. Apparently, white dwarfs have a tendency to collide with each other more frequently than originally thought. And one of the reasons for that is that, you know, unlike our star, unlike our sun to our current knowledge, the majority of stars out there in the universe exist in, they don't do social distancing. So you would get like a binary star, a trinary star, or whatever. So you'll get multiple stars orbiting the same place. And so the possibility of them colliding is fairly high. And so when these white dwarfs collide, it was found somehow, and it always boggles me how they find out these things, but it was found that the resulting supernovae have, they all basically have the same luminosity. They give off the same amount of light. And so therefore they can be used as what is called standard candles. And um, so these lights act as standard in the universe that astronomers can use to measure distances by comparing the standard candles, um, the if you know the relative brightness is an indication of how close they are, because the closer they are, the brighter they would be. The farther away they are, the dimmer they would be. Uh, it is an indication as to whether the galaxy is moving towards you or away from you because of the red shift that would occur in the standard candle. Because as I said, under normal circumstances, they basically give off the same light. So any variations that you detect in the light that is produced is an indication of something. As I said, whether it's distance, whether it's velocity, and so on. Also, these type 1A supernovae produce much of the iron and other metals that are in the universe. Now, when the universe started out, the theory is that it was primarily hydrogen and helium. There were no other heavier elements to speak of. But over the process of time, these elements are produced within the core of the various stars. And the supernovae is what is required to produce elements heavier than iron. Now, with a massive star death, um, that can also cause a supernova. And as we all know, stars have a lifespan. They're born, they shine brightly, go about their own business, and then eventually they die. Now, while the star is shining brightly and is stable, there's a balance between the gravity caused by the core of the star and the outward pressure from the reaction going on in the within the core. So I picture it as like a balloon. When you inflate a balloon, the tension in the balloon is trying to contract the balloon, and that would be kind of like what the gravity is trying to do. but the pressure of the air inside is trying to expand the balloon. And when you are blowing into the balloon, the pressure kind of wins, so the balloon expands. If you let some of the air out of the balloon, the the rubber wins, so the balloon contracts. And so similar with a star, uh, as the core is generating all these outward, this outward pressure, trying to expand the star, and the gravity is trying to pull the star back in. And there's a point where it reaches equilibrium, and so the star kind of remains the same size. Now, a massive star is, I would say, a star that is at least 8 times as massive as our sun. I hesitated there a bit because in reading different sources have different values for what the massive star is, but I will for now go with the 8 times. Now, when the star runs out of fuel, the pressure that is being exerted by the core drops and gravity wins. And I'll say here, the star, it's not that it runs out of fuel. As the star goes through its lifetime, it starts off as hydrogen, and the nuclear processes convert that hydrogen to helium, and then other nuclear processes kick in, which convert the helium to, I can't remember what comes next in the transition, and so it keeps converting and generating these new elements until it gets to iron. Right now, iron can be converted to the next element down. However, to do that will require more energy put in than what is released by the reaction. And so therefore, it doesn't happen, right? In all of the previous fusions, more energy was being released than was required to do the fusion. And so those processes were able to continue. But then when you get to iron, it would require more to convert iron to something else. So the process stops. And so at that point, when the process stops, that's when the pressure that's being exerted by the core drops, and the star collapses in a very, very short space of time, anywhere from less than a second up to, I saw one source saying 15 seconds. But even so, if you consider something the size of 8 times our sun collapsing in 15 seconds or less, that is quite an instant event, and the resulting shock wave causes the outer part of the star to explode, and that basically creates the nebulae that we will see when we look up in the sky. And this explosion liberates enough energy to create the elements that are heavier than iron. I said that the fusion process stops at iron because it requires more energy put in than what would be released. But this explosion generates so much energy that you have from iron all the way up to plutonium being created in that explosion and then flung out into space. So when you think about it, and again, this is quite an interesting fact, all of the gold on the earth, and I've read that there's enough gold in the earth to basically cover the earth. I think it was to 4 feet. However, a lot of that is down in the core. So unfortunately, we don't have streets of gold just yet. So the all of the gold on the earth, all of the aluminum, all of those things started life in a supernova somewhere, how many ever light years away, and flew across the universe, perhaps on a piece of rock, perhaps as a gas or something, and landed on the earth and gives us these minerals that we have today. Massive stars with masses, and again, here different resources had different numbers, but massive stars with masses less than 25 times that of the sun become neutron stars, where massive stars with masses at least 25 times that of the sun can become black holes. All right. Now, the pair instability supernova is a bit more complicated to explain fully. So again, we'll just give a brief description. So when you get really massive stars, stars that are at least 130 to 250 times the size of our sun, which as far as stars go, you know, there are stars like Betelgeuse, which I believe is a lot bigger than that. But anyhow, when stars that mass with a low metallicity die, um, and when they say metallicity in astronomical terms, in physical terms, the term metallicity refers to anything that's not hydrogen or helium. So you have, it's not necessarily a metal as we know it. You know, it could be carbon, could be beryllium, boron, whatever. But stars are that have low metallicity, so they're primarily hydrogen or helium, and have masses between 130 to 250 times that of the sun. What happens? They can get so energetic, the processes going on within them, that the gamma rays that are produced have so much energy that instead of creating the outward pressure that keeps the star inflated, the energy in these gamma rays basically collide and form what they call electron positron pairs, or another resource said matter antimatter. So, and then these pairs, they 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 combine and they can create an explosion that annihilates the star. So whereas with the previous types of supernovae, you would have a, a black hole or a neutron star or something like that remaining, with the pair instability supernova, basically nothing remains. Everything is just dispersed out into nothingness. So now we're just going to look at a couple of slides of what remains of some supernovae. This is an image of Kepler supernova, which was the last supernova observed in this galaxy with the naked eye. And this was observed in 1604. Now, prior to that, there are records of supernovae being observed by, I think it was the Chinese, I think around 10 something. And then also some supernova observed before in the BC era and so on. But the last supernova observed with the naked eye in this galaxy was in 1604. And this is what remains of it. This is Kepler's supernova. And that's why I was so kind of disappointed when David said that it's unlikely that Betelgeuse is going to explode. Because if Betelgeuse was to explode, that would undoubtedly be seen with the naked eye and be in this galaxy. But alas, apparently that is not to be. Now this thing that they call, it's apparently pronounced assassin, ASASSN 151H. This explosion, it was in a galaxy 3.82 billion light years away. And it was 20 times brighter than the Milky Way and 570 billion times brighter than our sun. Supernova 1987A, first observed, surprisingly enough, in 1987, February 23rd, actually, which is 34 years ago today, precisely. This supernova was 160,000 light years away, and it was the brightest seen since 1604. And this supernova created a sort of a ring, actually 3 rings. You can see one brighter central ring and 2 dimmer outer rings. They kind of explained how those rings were formed, but I can't remember all the details now, so I won't go into that. Now, supernova 2006 GY, which was some 250 million light years away, appeared, of course, in 2006, and was one of the brightest ever in terms of energy output. And it's believed that this was a pair instability supernova. Now, as I say in the fine print there, the blob in the upper right hand is the supernova. Well, they call it a hypernova. And the blob in the lower left is galaxy NGC 1260. And so I mentioned that supernovae, when a massive star, at least 25 times the mass of the Earth, goes supernova, it can create a black hole. So what are black holes? A black hole is a place in space where gravity is so strong that not even light can escape. Now, gravity is so strong because a large amount of matter has been squeezed into a tiny space. Now, it's black because of the absence of radiation, but it's not really a hole because it has mass. You know, when I think of a hole, I think of just a gap, a nothing, a space. But a black hole has a mass, so it's not really a hole. But anyhow, the intense temperature and pressure at the core of the collapsing supermassive star is sufficient to disintegrate the atoms of the star and cram them into a small space. So a star with a diameter of millions of kilometers can be crushed into a ball 1 kilometer wide. Now, just to go into a little physics here, when we've all heard of atoms, and atoms have a nucleus and has electrons whizzing around it and so on. And matter is made up of atoms. Molecules are made up of atoms. And the distance between atomic nuclei, the nucleus of the atom, the distance between the nucleus of adjacent atoms in any object is relatively large when compared to the size of the nucleus, with electrons whizzing around the nucleus, keeping the two nuclei separated. Now, when the supernova occurs, the forces are intense enough to kind of like strip away the electrons, etc., and push the nuclei together somehow. And this, because the space between the nuclei is so large relative to the nuclei, when you push the nuclei together, you can get a much smaller, it occupies a much smaller volume. And so you end up with something being extremely, tremendously dense. And if I can make a reference back to the movies and pictures like Ant-Man and so on, that miniaturize people or miniaturize objects. If you miniaturize an object, unless you eliminate some of the atoms, you're just reducing the space between the nuclei, but the mass is still there. So if I was miniaturized down to the size of a Ken doll, I would still weigh about 200 pounds. So that would be one extremely heavy Ken doll. And in the same way, when a star is collapsed, it may occupy a small volume, but it is extremely dense because the mass is still there. And I said I was throwing this little equation here just as an illustration, which really, this equation relates to the force that gravity exerts on a mass resulting from the gravity of the Earth. Right? So it's F equals small m gm over r squared. And why I said I would throw this in, don't pay too much attention to the actual values of the numbers, but just by looking at the equation, you can see that r squared in the denominator is the radius of the Earth. And so if we replace that with something smaller, because you have a smaller number on the denominator, the value becomes bigger, right? And especially since you're squaring that number, the effect of reducing that can be quite significant. And the big M on the top is the mass of the Earth. So if we replace that with a much larger number, the force will be much larger, right? So we don't really have to concern ourselves with what the values are, but we know that just by looking at this equation, if a black hole could have a diameter of a couple of kilometers, which is much smaller than the diameter of the Earth, but has a mass of billion times or more of the Earth, then the force of gravity that that black hole exerts would be trillions of times that exerted by the Earth. So if you, I just put that in there to show you the, so you can kind of get a sense of why the the force of gravity on a black hole is so high. Now, the event horizon of the black hole is the boundary at which light cannot escape. Its radius is called the Schwarzschild radius, after uh, somebody Schwarzschild, and it is proportional to the mass of the progenitor star being the star that collapses to become the black hole. And if we have a black hole with a mass of 10 suns, the radius of this event horizon would be 30 kilometers. So that means that the light can get to within 30, can get to as close as 30 kilometers to that black hole and still escape. But if you get to 29.9 kilometers, well, you're a goner. There's no escape for you. Now, some black holes that, especially those that are sucking in material that are near to it, like those with the companion stars, etc., can superheat that material that they're sucking in to the point that it radiates tremendous amount of X-rays before it enters the event horizon. And so, you'll see images of black holes depicted like shooting beams out of the top and the bottom, like this image here. And you'll say to yourself, well, I thought that nothing can escape from a black hole. How is it able to shoot a beam? But the beam isn't coming from the black hole itself. It's coming from the material that is about to get sucked into the event horizon. And it can be quite an intense and powerful beam. Supermassive black holes are believed to be at the center of galaxies. And so, for example, our galaxy, the Milky Way, is believed to have a black hole called Sagittarius A star with a mass of more than 4 million suns. So you see that is quite a big black hole. And in 2019, for the first time, a supermassive black hole at the center of the galaxy was imaged. And this was at the galaxy M87, which is 55 million light years away. And this black hole is believed to be 6.5 billion times the mass of the sun. Now, in the image there, you can see basically the hole in the event horizon, and you can see that one side of the event horizon is tending to glow brighter than the other side, and according to the write-up, that is because of the rotation of the black hole, which is causing kind of like a Doppler effect on the particles. So the particles that are basically heading our way appear to be more energetic than the particles heading further away. And that basically is the end of the presentation. I would advise you not to think that you can fly into a black hole and come out in another part of the galaxy, because I suspect that if you fly into a black hole, you're not going to come out anywhere at all. And so with that, I will hand you back over to David.
Well, thank you so much, Max. That was a very thorough and insightful presentation you delivered there just now. And I really do appreciate all the time and effort that you had to have spent doing research and preparing that presentation. In fact, both of them. Yeah, I mean, clearly, you know, it also, I remember when we first broached the idea of presenting on supernovae and black holes, we were thinking about how complex a subject it would be. But you took your time and distilled it down to layman's terms, and I'm sure that many of us who heard it really did get a firmer grasp of what black holes and supernovae really are and what they're all about. I really do thank you. I don't have any specific questions per se. Well, two things really. This actually is the start of our open discussion session. So anyone who would have heard the presentations before, you could feel free to ask any questions about them. And of course, you can discuss any topics related to astronomy. The other thing though, is that I really do have to go and check on a couple of things, because remember, if all goes well, I intend to stream for everyone to view that lunar occultation that's happening tonight. So I do have to go and check on a few things and hopefully set up in order to provide that live stream. All right. So with that, I'll basically open the floor to the discussion, and I will chime in to let you know what the status is, whether it's a go for the live stream. Chances are if you don't hear me in another 10 minutes or so, I'm actually setting up for it. So that's a good sign. All right. So, well, Thomas, do you want to take over as host in the interim?
Sure, thank you, David. No, I'll be happy to do so.
All right, thanks. All right, so I will be back in a few.
Okay, thanks, David. Anybody has any questions on anything we've discussed so far?
Hi, Thomas. Can you hear me?
Hi, Lee, yeah.
Okay. Max, I have a question. You described supernova as the explosion of a star, right? Max?
I'm here.
Right, but what is a nova?
Okay, I was kind of hoping you wouldn't ask that question. I actually do have, I did make a note as to the difference. Let me pull it up. From what I was reading, the nova was basically any explosion on a star. But let me try and find what I actually wrote down for you. All right. All right, well, I'm trying to find this in my notes.
Well, I have another question. Maybe Thomas can tackle. But this is just I guess a reminder of some things. Because in your presentation, you were speaking of some of the events. I think 2006 GY was 250 million light years away. It was something like that, I think. But that's essentially the amount of time that it takes for that light, for that event to reach us. So that happened a long time ago.
That happened era of the dinosaurs.
Yes.
But we would be seeing it back then, but we see it when the light reaches us. But it would have left there 250 million years before.
So what we would have seen it back then?
No, we would have seen it when we see it. We see it when
Right.
it reaches us,
When
but
it reaches us,
what we are
right.
observing took place 250 million years ago.
Yes. Yes.
Right.
Kind
So
kind of mind-boggling.
It is.
this thing, stardate.org basically said a nova is an explosion from the surface of a white dwarf star in a binary system. Supernova is a violent stellar explosion that can shine as brightly as an entire galaxy of billions of normal stars. So the impression I got from that is that the nova does not necessarily result in the destruction of the star,
Yes. Yes.
whereas
Yes.
supernova does.
Does. Okay. I just wanted.
Um, uh, can you hear me, Max?
Harry,
Oh, Max.
I can hear you.
Yes. Now, to add further weight to the differences between the supernova and the nova, as you said, the nova happens in the binary system. Now, what that means is that in a binary star system where there's a much larger star being orbited by a smaller white dwarf star, it sometimes happens that the white dwarf because of the more concentrated gravimetric field, the white dwarf tends to pull material off of the larger parent star. That material falls down onto the surface of the small white dwarf star, but the star cannot really manage the amount of infalling material. And the star basically gets a hiccup, or basically gets indigestion and explodes because of the massive amount of material falling onto the star's surface, and that is a nova. Now, that is many orders of magnitude less violent than the supernova, which basically is the death of a massive O-class or B-class supergiant star, you see? So that is basic difference.
Okay, thanks, Ricky.
Okay.
Thanks, Max.
Okay.
Any other questions? Max, I thought you did a very good job on a very complicated subject. So thank you very much for that. We are currently waiting to hear back from David, who is checking his equipment, and he's also checking weather to see if he can see his occultation.
I have a question, which perhaps Ricardo can answer. Because as I mentioned in the presentation, we can't see. It's difficult for us to see supernova in our own galaxy because of the the dust. So how is it then that we can see a supernova in another galaxy? Wouldn't the
But
same dust?
the basic answer to that, Max, is that we don't see many supernovae in our galaxy because basically supernova are really a rarity in our galaxy, about 2 every century, basically, in our galaxy alone. Now, typically, when a supernova occurs, it outshines all the other stars in the galaxy. It has that capacity to basically outshine the stars in the galaxy. For example, in 1987, I believe it was, a supernova occurred in the Magellanic Cloud, which is a small galaxy orbiting Earth, about 100 and, I believe, 69,000 light years away from us. And it was seen in the southern sky. As a matter of fact, it was at the limit of human visibility, which is around magnitude 6. Now, we can record galaxy supernovae in galaxies far, far away because they're so bright. Telescopes, the big telescopes, see galaxies going on and see supernovae going on in galaxies millions of light years away, because the output of energy from the supernova is so large. So it's not a matter of dust as such, right? Because a supernova is bright enough to shine most dust clouds. As a matter of fact, you know what I mean? When the supernova goes off, all the other stars in the galaxy are put to shame, even with their own combined magnitudes, right? Such as the magnitude of the supernova. For example, if our favorite star Betelgeuse were to go supernova now, it would be an unmistakable event, and it would be seen basically all over the galaxy. If you were at the end of the galaxy, basically if you were at the other end of the rim of the galaxy, with a line of sight between Betelgeuse in our quadrant and your side of the galaxy, you would see Betelgeuse. You would see the explosion when that went off. If that answers your question.
Yeah, that was basically some of the information that I read was kind of misleading.
Not only that, Max, it will also be outputting energy in other wavelengths apart from visible light. And undoubtedly, some of that energy will be in the infrared, which is heat. And heat is visible, infrared is visible through dust. So dust blocks visible light, but it doesn't block infrared. So, if we were looking at a supernova, we would be able to see the infrared even if we didn't see the visible light for whatever reason. So we would see it in other wavelengths. See, if it's because the energies are so large in some of these things, we'd be seeing them very bright in the X-ray or even gamma ray.
Yeah. Another signature of a supernova really would be the massive surge of neutrino radiation, which is particle radiation caused by the massive interactions that were going on at the core of the star. Now, the neutrino emissions usually precede the actual supernova itself by perhaps a day or so, right? But you would also, if you had a neutrino telescope, you would see a massive surge of radiation. So as Thomas said, the supernova will radiate at various frequencies that are, will be transparent through the dust haze or whatever it is there might be in your line of sight. So, a supernova basically would be virtually, it would not be secluded at all. It was something that would be unmistakable in your sky.
Though on that point, neutrinos are hard to detect on Earth because they interact with matter so little. Though there are neutrino detectors, I believe the big one,
right?
The Antarctic,
yeah,
under the ice. There's a neutrino.
Yeah, they're
because
yes.
now the Earth is bombarded by trillions of neutrinos, and the interaction is very small. You may have one neutrino interacting in
one or two, right?
In a year, where the trillions passing through us every second. Yeah, but yes, okay. David has just said to me.
You see the neutrino.
Yeah, go ahead, Ricky.
Hello. Yeah. What I was saying is that the neutrino telescope basically works on a basis where, you know, as I said, there's a massive underground vat of Clorox probably, and there are detectors all through the vat of this vast volume of liquid. Now, when a neutrino comes in, obviously the neutrinos would, as far as the neutrinos are concerned, they're so energetic and so small that even the core of the Earth will be empty space to neutrino. But as per chance, a neutrino might collide with a chlorine atom and change that chlorine atom into an argon atom. And the detector will basically detect the argon atom creation and signal the presence of a neutrino. Now, if enough of those collisions occur, we would know that in a specific part of the galaxy that we will be able to pinpoint that either a supernova is happening or is about to happen, right? So that is the usefulness of a neutrino telescope. But as Thomas said, they are rarity, and it is very hard to detect a neutrino when it passes through. Very, very hard indeed.
Okay, Ricky, thank you. David has let me know in the chat that we are a go. I'm just waiting for him to come back onto the Zoom meeting. So as soon as he's back on, I will give him the host and we will be able to see through his instrumentation, this occultation.
So while you're waiting for him to come back, Thomas, can you put up the QR code or whatever it is you're going to put up?
Okay. Yeah. What Max is talking about is if you are interested in membership with the Barbados Astronomical Society, one way of doing that is you can email. I'll put it in the chat. You can email admin@hbo.bb for information on membership. And there was a QR code that if I can find it, I'll have to look for it. You can scan that on your phone and it takes you to a application form. Okay, sorry, I'm getting a link here. Let me just, right. There's a link in the chat as well. Right. If you look in the chat, there's a link to a Google Doc that will also, if you fill in the form, essentially your information for membership will be captured. Membership fees are $100 Barbados for membership, for a full membership for a year. And there is associate membership at $50 a year. And membership fees are essentially what keep us going. Certainly at the moment where we are unable to do paid events on Friday nights that we normally do. Because of the whole COVID-19 situation. So, you know, if you do, I'm sure we can take your fees for membership through a direct bank transfer. That information could be made available if you are interested in becoming a member. So you can have a look in the chat to see the link to the Google Docs. You can fill in for that. Thank you, Max, for reminding me. We're still here waiting on David. I am just wondering if I should give him a call.
Thomas, could you let people know what people will get from the membership? I mean, we're closed now, but once we're open, what does a membership entitle you to?
Certainly. One of the things we try to do is we have membership evenings like this. In normal times, we would do this on a Tuesday night at the Harry Bayley Observatory, where we will have discussions on various topics. We also will offer, we do offer training in terms of basic astronomy, how to use the telescope, how to set up and use the telescope that we have there. The main telescope or one of the smaller telescopes. We do some of the theory. We sometimes do some experiments where we're able to, you know, take certain measurements. We've done so in the past where some of the measurements have actually been published internationally, things of that nature. We from time to time have social events with our members, particularly at Christmas time. We'll have get-togethers and so on. I mean, things that we're forgetting about because of the whole COVID situation.
As well as entrance to the observatory on Friday nights.
Yeah, that's included in the membership.
Exactly.
Anything else that you want to do? Because I just want to give David a call to find out what's happening.
I can't think of anything, but I would like to say thanks to you and Max for your presentations this evening. I thought they were really good. Does anybody have any questions about what we discussed this evening, or in general about the observatory or the Barbados Astronomical Society?
Well, Lee, no questions, but I also just wanted to concur with you that the presentations were really good. And for someone who is very much lacking in knowledge, I was able to follow. So thank you both.
Nice to hear from you, Sally.
Nice to hear you too, Lee.
Anyone else?
Yeah, my name is Bruce. I would like to congratulate Thomas and Max for their presentation. I came on a little bit late because I had the wrong code, but anyhow, Thomas, your how you put the things in realistic as to the distance of our solar system was very, very interesting, and yeah, it really shows how vast out there is. So that's all I have to say. Thank you very much for your presentation. It was very good. Thank you.
Thank you, Bruce.
Thanks, Bruce. I didn't get David on the phone, so I assume he's outside onto the telescope. So I guess we just have to be a little bit patient. Guess we just have to be a little bit patient. I'm not sure what the issues are, but knowing David, he would record it. So if anything, we should be able to see it a little bit after the fact.
Is there anyone that got an opportunity to see the footage of the Perseverance rover landing on Mars? That was an exciting event that happened this week. Thomas, did you see it?
Yeah, I saw it. I thought it was very fabulous, and it's an interesting project. We'll see what they come back with. Some of you may or may not know, one of the key things in this project is to actually drill some samples, analyze them on the spot, but also store them away so that a future mission can actually return those samples to the Earth sometime around 2030, which would be the first time that we are returning actual samples. I'm sorry, it's not the first time. We return samples from the moon. We return samples from an asteroid, but it'll be the first time we'll be returning samples from Mars. And the area that the spacecraft, the Perseverance, landed in is thought to be an old delta where water, an old lake, it's a lake bed where water flowed in and water flowed out, and where the water flowed in was a delta, and that's basically where they've landed. And they think that may be a good spot to take samples from, that they may be fossilized microbiological remains.
I have a question for you, Thomas.
Yes.
since you work at NASA,
Here's David coming back on. I'm gonna, Max, I'll hold the question. Let me get David. Hi, David. Good to have you back. Are you hearing me?
Hello, hearing me now?
Hi, David. Yeah, good to have you back.
Hi.
Do you
Yes.
make you host again?
Yes, please.
Okay, there you go.
Great. All right, so I'm going to share my screen. See what's happening. All right. Okay, so what you're seeing here is a live view of the moon, and well, that little dot right there, that would be the star in question. Kirkup, Gamma, oh, sorry, Kappa Geminorum. So, just for everyone to understand, right now the moon is orbiting the Earth, and it's actually, from this view, it's going in this direction, such that eventually the dark side of the moon, you can actually see the outer extent of the dark side in this shot, right? But appreciate that it extends beyond the terminator line. At any time after 8:35 p.m., we expect that dark side to cover the star, and well, you will see what an occultation of the moon, of a star by the moon, sorry, is really all about. It won't appear to set or gradually disappear. In less than 0.1 seconds, it will just be out like lights out, maybe faster than natural light turning off. And the key thing here too is that the timing of these events, like I said, I know that it will happen sometime after 8:35, but it does vary heavily depending on where you're observing the occultation from. Astronomers around the world, they measure the timing of these events because it gives them a better appreciation of the level of accuracy they have in the models that they currently use to predict these events, and also the models that they use to, well, estimate the current location of the moon, because depending on how close the moon is to Earth right now, the size, the apparent size in the sky will change, be different. So the timing at which the moon would appear to occult objects in the sky would be different. Right? So even as I'm saying this, I'm finishing the setup here because I have to turn on the timestamp. All right, so the idea is that I'm going to record this occultation, and then shortly after, I'm going to have to report what I've recorded. This Astronomical Society, the Amateur Variable Star Observers Group. They collect this sort of data, and it's useful then to the global astronomy community, because when they analyze the results of these observations, it then feeds back into the tweaking of those models that I spoke of before. It's rather windy out, rather chilly, but there is a break in the clouds, so just trying to take advantage of that. The scope is up perfectly aligned, so that's why I have to occasionally adjust the view to keep things aligned. Because right now there are clouds covering the North Star, and I would have normally aligned the telescope on the North Star for proper tracking and guiding. Just trying to make do with what the current situation and scenario provides. All right, so are there any questions at this point as we view?
Those of you that may have missed the initial part of the presentation tonight, David explained the occultation with this star. It basically means the point in time where the moon covers it, blocks it. And he's actually got this is live through his telescope in his backyard. And as he said, these observations are important in terms of testing our models. So he's going to record this and make a note of the exact time that it disappears, which helps to position the moon and things of that nature.
All right, so I'm going to start recording right about.
I'm sure you could appreciate the challenges of being out there in the breeze.
Yeah.
This is what happens in the real world. You get clouds, you get rain, you get breeze. Hope you're not running out of space on your drive.
Do exchange. That should capture something. So we have some clouds coming over. That was interesting just now. Well, granted the recording has started, but now we have some clouds.
I don't know if this is applicable, but how fast does the moon move?
Right. So when we observe from Earth, what we normally report in terms of the motion of any object across the sky is normally with reference to arc seconds. So, okay, well, I know there's an actual velocity, an orbital velocity of the moon. That's one thing. But for the purpose of measure occultations, we know that the moon would, on average, appear to move at 0.55 arc seconds per second across the sky. A star is roughly 0.057 arc seconds in diameter. That's why when the moon when it blocks the star, it will take around 0.1 seconds to disappear because it's covering that diameter of the star in 0.1 seconds because the moon moves at 10 times, well, at 0.55 arc seconds per second. But if anyone else can look up that actual orbital velocity of the moon quickly, that would be cool. Right now the cloud is okay, good.
Thanks for that. It was very interesting.
Sorry. Yeah, okay.
Well, the star probably should be covered by now. No, is that
Oh,
there? It's
still there.
visible?
Still there, it's just clouds,
Cloud.
intermittent passing clouds that I hope do not, okay, it's still there. It's still there. What is the... 38 still there. was hoping that we capture that moment when the star disappears. It doesn't happen while we have cloud cover. But as you said, Thomas, this is the reality of astronomy. We're at the mercy of the weather for ground-based observations.
Yeah.
And it's still there. Okay. All right.
The mean orbital velocity of the moon is 1.022 kilometers per second, according to Wikipedia.
Well, thanks, Max.
What this sort of also demonstrates is what a lot of astronomers do is they rent time on powerful telescopes, and they can basically access them through their computers, like kind of how we're seeing David do right now. And so a lot of astronomers, certainly in various parts of the world, could rent time on telescopes down in Chile or in Australia for some of these observations. So they don't necessarily have to go to an observatory near where they are. But as you would imagine, the competition for time on these telescopes is fierce. So a lot will depend on your reputation and the project and the amount of money involved and all sorts.
Last bit of cloud cover. The star is gone. The occultation actually happened during that last bit of cloud cover. Did you not? Now, behind the moon, and the best estimate I could give is that it would have happened during that period where the cloud had passed. Anyway, that is okay. Right now, there's a whole lot more cloud that is covering over the view. So, all right. So whereas this did not quite give the result I would have liked, I think it is a useful exercise, and I think so long as we're having these virtual sessions, if at all possible, if we could at all build in a similar viewing session like this, because this does provide that sort of window into the actual work of astronomy. The imaging, the collecting data, the understanding the significance of it. And in addition to, I mean, there's so much that even the basic average person who has an appreciation of the sky that we can actually show anyone out there, provided the weather cooperates, that it makes for a far more informative session. You got the theory, and then you actually see some of the work in practice.
But David, how often? Because I would imagine with all these with all the stars that there are out in the sky, um, admittedly we can't see all of them, but we can still see what 4,000 or how much hours it is we're supposed to be able to see. Shouldn't these occultations be a relatively frequent thing?
What do you think? Well, granted, I mean, occultations will happen, just by definition, whenever the moon passes in front of the star, it'll be occulted. However, the number of naked eye visible stars the moon will occult, it's far, far fewer. And this, as I said earlier, if you had a pair of binoculars, you would have basically been able to see something very similar. I would say that it might have been easier, of course, if we had a little less haze in the atmosphere, but I think you get that appreciation just by being able to be under. So whenever there's an opportunity like this, whenever there's a naked eye visible star that's being occulted, it is an event that you can easily share with everyone. It's not, you don't require the high-end observing equipment to see. Also say that, you know, that the moon will appear to vary only by 6.5 degrees from the line of the ecliptic. So there's a very finite set of naked eye visible stars that it can occult, right? Luckily, there are some prominent ones. Regulus, Antares, same star in Eta Leonis in Leo, this Kappa Genorum in Gemini, and there are like two others that, yeah, on an annual basis, yeah, you get that occultation happening. But then again, occultations aren't visible from every point on the face of the Earth. We saw it here in Barbados. Persons in as far north as Florida may have seen it, but anything north of that, no. And any location south of Venezuela would not have seen it. So those observing sites that lie along that narrow path of visibility, you know, we're duty bound, so to speak, to try to record the event and share the timings, because it's really, like I said, the information is very useful.
Totally unrelated question. And the moon has gone off of the screen now.
Yeah, let me see if we can at least take a view of the moon.
So those three craters there that are close to the whatever you call it.
Terminator.
Yeah, those three craters close to the Terminator, on the lower side of the image. Yeah, those. Do you have any idea how wide those are?
It can be worked out. I would say that these are probably somewhat bigger than you would think, probably 250 and 100 kilometers. But yeah, based on the current distance of the moon and the arc second, the length of the sky, so to speak, that the greater span, you can work out the dimensions. Of course, the accuracy will vary depending on the obliqueness, the angle at which the crater appears to us, but you know, you can work it out with some measure of accuracy.
Well, with the diameter of the moon being some 3,400 kilometers, you could do a pretty rough calculation.
That too, yes. Yep. Right.
Well, you answered my question. If you said it's in the order of 100 kilometers or whatever, then no, I was just wondering if we would have been able to see something in it, like if there was a rover driving around or something. Or,
No. Actually, maybe remember I had shared on the WhatsApp group that extremely large telescope that is under construction in the Atacama Desert in Chile. That might be able, with its resolution, that might be able to pick up the rovers and the remnants of the Apollo mission. But all other ground-based telescopes, they lack the level of resolution to, to pick up objects as small as that. But having said that, the scope that I'm using right now, this is a very small scope. This is 102 millimeter diameter aperture, which is why I was able to get that view of the moon and the star at the same time. Bigger telescopes, the bigger the scope, the more the aperture, the more resolution you'll get in your images. So, we have opportunity once this COVID situation passes us, then using the 16-inch telescope at the Harry Bayley Observatory, you'll be able to get much more detail. Even for these simple Zoom sessions, you'll be able to see far more detail on the surface of the moon.
My final question, which is the question I was going to ask Thomas before you go, but whichever of the two of you work at NASA can answer this. With the probe on Mars, the Explorer. I know they had said that they're going to have this little helicopter flying around, but they also said that it takes 11 minutes for the signal to get from Mars here. So I was just wondering if the flight of the helicopter will be pre-programmed, because I don't think that you'd be able to with a 11-minute lag one way be able to sit with a joystick and control it. So exactly how do they plan to use this helicopter on Mars?
All fully autonomous.
It's autonomous, but I think they sort of program in a general set of directions, and the helicopter will then make its own decisions based on that, using artificial intelligence. And I mean, they basically has said that this is a test of the technology. I also, something I discovered the other day, it can't fly for very long because of the amount of power required. I think it can only fly for a matter of a few minutes, and then it's got to land and recharge. But it's a proof of concept at this stage. They're just trying to figure out if they can do it and what the problems are. No, you cannot. Certainly with a 22-minute round trip time, there's no way you can fly that thing from Earth.
I think that the early rovers, they did have to execute that level of patience, no, and dedication.
Oh, yeah.
They used to give the command to move 2 feet, and you waited. You waited the 22 minutes for confirmation that it moved 2 feet. But things are a whole lot better now. The technology has advanced here.
If you think about it, we're on the verge of self-driving cars. So why not on the verge of self-driving, self-flying helicopters on other planets? What a time to be alive.
Correct. Correct. The technology there is advancing so rapidly. Once they get that, and I know it will be a success. I am more than certain that will be successful one way or another. Whatever they learn from that exercise, I am sure that in 5 years time, because that technology could then be used not only here on Earth, it's sort of it's really fully autonomous guidance of an aerial vehicle. You'll see it here on Earth first, and then you'll see the advanced version deployed to Mars when we finally start to land astronauts there.
David, I was gonna suggest you come out of the wind, being that.
Oh, the audio is choppy?
Yeah, it's can hardly hear you.
Oh dear. Okay. All right. Wow.
But I mean, on David's point, there is a plan to send a robot to Europa, and it may very well have an aerial vehicle on it as well. It may have a submarine on it. So again, we need to take this technology as far as we can in terms of the machines being autonomous, because there's no way you can control something on Europa from the Earth. The light time there is, I don't know, I have to look it up, but it could be a matter of hours. So those machines, you have to fend for themselves. Any further questions? Any ideas? Any observations? Any requests? I have a question there on the chat. What is the most interesting body in the solar system? Well, there are many. I don't think there's one. I don't think there's one. Certainly, we are learning a lot more as time goes on about the bodies in the solar system. The reason I think there's a big focus on Mars is because Mars is relatively close to Earth. And we can get spacecraft and robots there. It'll be much more difficult. We landed a spacecraft on what's the name of that moon? Oh Lordy, on
Titan.
was
Titan,
it?
right? I think
Titan.
Titan.
Yeah. And that's one of the moons of Saturn. Am I correct? Yeah, we landed a spacecraft on Titan, which is a moon that has liquid methane lakes. So, I mean, you know, that. There may be other things like that. I mean, a lot of it comes down to the amount of money you have to spend to do this, because these projects are extremely expensive. But certainly things closer to the Earth, like Mars and the Moon, you know, it's easier to get things there. I mean, if you look at it now, India has been to the Moon, China's been to the Moon, Russia's been to the Moon, the United States has been to the Moon. I'm not sure if Japan have been to the Moon. They might have been. You know, so other countries are becoming interested in getting probes on the nearby planets. But as you can see from the sort of discussion I did in the presentation on the distances, you know, even though the solar system is our immediate neighborhood, things aren't that close. You know, it takes a lot of time to get spacecraft there and a lot of money. So I think we tend to have to pick and choose the projects very carefully. But
I think I'm a bit biased, Thomas, but I think Earth is the most interesting body in our solar system, because if we were to find on one of the other planets even the minutest fraction of biological complexity that we have here, it would be incredible. So I think we're the most interesting.
okay, interesting observation. Yes.
I mean, who is more interesting than us?
Well,
That's a fair point.
currently we don't know.
Well, I mean, given just like preliminary observations
Yeah.
of what we do know, I think the action is all here right now.
Yeah, but I mean, you know, if you think about it, we're at the very beginning of this type of exploration. You know, we're like the Stone Age man on a log with a paddle, wondering if he can get to that island over there that he can't quite see. You know.
True, but what we're looking for are essentially planets that are dusty and, for all intensive purposes, on the initial observation, dead.
Yes.
Earth is not like that at all.
No.
Earth has got life just flourishing all over it.
Yes, indeed. But I mean, don't forget too, with the exploration of the exoplanets. You know, I mean, we're finding Earth-like planets, and we're trying to build instrumentation that would allow us to observe them more closely. There's a question here from one of our folks saying, do you guys think there's life elsewhere in the universe? Nice controversial question. I will answer it by saying this. There's something called the Drake equation, which was a fellow by the name of Drake developed it in the 60s, and he basically tried to compute the probability of life elsewhere in our galaxy. And that's something worth looking up. You can do a Wikipedia on the Drake equation, and I believe it has been revised more recently with some of the, at the time when the Drake equation was formulated, we hadn't found any planets orbiting other stars. The only planets we knew of were the planets orbiting our sun. We now know that many of the nearby stars to us that we can observe pretty closely have all got planets orbiting them, and some of them have planets orbiting in what's called the Goldilocks zone. That is a distance from their star such that the temperatures on the surface of the planet allow for liquid water. So with the advent of the James Webb Telescope, hopefully to launch later this year, one of the jobs the James Webb Telescope will be doing will be actually looking for signs of water on some of these planets. And obviously, if we can find water in the spectra of these planets, you know, it may suggest that that is an area where, you know, life may exist. And, you know, maybe with a future space traveling technology that we don't currently have as yet, we may be able to get to some of these nearby stars. You know, we currently can't do it. It'll take too long. But there are some very, what shall I say, some very creative minds working on the problem. But if you look at the numbers, the fact that we now know that most stars appear to have planets orbiting them, some of them will have planets orbiting in the Goldilocks zone, and we have somewhere between 100 and 200 billion stars in this galaxy alone, which would suggest that there are over 200 billion planets in this galaxy alone. You know, the numbers, I would think that we are not likely to be the only place where life exists in our galaxy or even in our universe. We don't have evidence of it as yet, but I would think the likelihood of life existing elsewhere, the probability of life existing elsewhere in some form or fashion, I would think is fairly high. But that is my personal opinion. That is not an opinion of the Harry Bayley of the Barbados Astronomical Society. That's an opinion of Thomas Clarke. Hope that answers your question.
I do enjoy looking at the moon like this.
Yeah. Just going to say that you can notice that, well, two things happening. Really, the winds are dying down, so the scope itself is vibrating a little less, but also because there are fewer clouds passing now, the atmosphere is less unstable, so the view is steadier. It's nice. That's the thing. This time of the year is often the best time to be viewing anything in the sky because the cooler temperatures tend to render the atmosphere more steady, because throughout the layer, from the ground layers of air all the way up to the higher levels, it tends to be less drastic changes in temperature. So the atmosphere is steady. You get these nice clear views. And in contrast, during the summertime as well, it looks, you know, some of the views look as if you're looking straight through water. Everything is very wavy and shaky.
And one of the things that is useful to note is when that area where it goes from light to dark is called the terminator. But if you look at it when you're getting at an angle like this, it becomes extremely three-dimensional. You can start to see the height and the depths of some of the the craters. It becomes very,
That's
very
right.
three-dimensional at that location because it's being side lit as opposed to being front lit by the sun.
And just the same way that there was a question earlier about the diameter of the craters, there are also methods that use, like this is an example where you have a peak on the crater's rim and it's casting a shadow. You can actually calculate the height of that peak based on the length, the apparent length of the shadow in the background. It's all very cool. So much that you can actually see and determine just by observation. Once you know how to do how to translate those observations into useful information, you can do that. And you'll be amazed at what you can learn.
So, David, what amount of the moon, what slice of the moon are we seeing here in the screen, would you say, a guesstimate? 20%?
For this area here?
That we're seeing on the screen, yeah. Is that 20%, less than 20%?
Okay, this is probably maybe 30%.
30%?
Probably 30%, yeah. It's just to say that, oh gosh, wait a minute. This is actually
that big crater is like about a 1/8 to a 1/10 of 30%. So we could work out the size of that big crater. Say it was a 1/10 of 30%, which would make it
3%.
I think he's working out the
that would make that crater approximately some 11 or 12 kilometers across. The big crater that your cursor is on, that's going to make it somewhere around 11 kilometers, very approximately in diameter.
Yeah, I suspect it might be a little larger than that, but it's okay. It's just to say that because if I were able to get a better fix on the overall view, because right now it's in gibbous phase, right? So it's, if this were closer to full moon, then the estimates would be far more accurate.
Yeah.
But in gibbous phase, it's I say 30%, but that is my very rough guesstimate, because this is not even, because a significant amount of shadow area still remains. Oh gosh, it's gone now, but it still remains on the side of it. Anyway, these are sort of things that, because they're actually pretty straightforward calculations that you can use to.
Very roughly, so that crater is like half the length of Barbados. Very roughly.
Yeah.
I mean, it's a rough calculation, but I mean, as you said, that full moon, you can do a more accurate calculation.
The moon being bombarded by meteors, or is it the occasional meteor?
Well, that all depends on the size that you want to refer to, because there's always the moon lacking in the atmosphere. Any little bit of debris passing by will, if it's on a trajectory towards the moon, it will collide with the moon, right? I would say though, sorry, go on.
If I was to build a base on the moon, how likely is it to get hit by a meteor?
Right, so actually pretty darn likely. Small bits of debris. I won't call them, it won't be classical meteors per se, because micrometeorites, things in space are always being impacted by micrometeorites. But things in the order of the grain of sand and larger that we would normally see burning up in our atmosphere, they're fewer. They still do happen, but you can appreciate the amount of damage that can happen if even something as small as that, traveling in the order of tens of thousands of kilometers per hour, the sort of energy released on impact, you can easily cause severe damage to a structure or a person, astronaut. So if you're struck that way. You know, I was going to make the point that during meteor showers, sometimes when you're monitoring, if the moon is in a crescent phase, you can see occasionally impacts from meteors on the dark side. Those impacts, they happen again. They're releasing so much energy that they do have that quite clear momentary flash of light. And you know that was a meteor striking the surface of the moon. So if ever you want to look out for it, if like the Geminid meteor shower and the Perseids and Lyrids to some extent, those meteor showers that have many meteors per hour passing into our atmosphere, that is a reflection of how much debris, well, how many meteors, sorry, are actually in that meteor cloud at that point in time. And that increases the likelihood that they would be impacting on the surface of the moon. They're easily visible. If you're watching it carefully, yes, you would be able to see those impacts when they do happen on the surface of the moon.
What would we do if you were to build a structure on the moon? You know, like we have the space station. I mean, would we build it on the ground, or do we build it strong enough to deal with these smaller impacts? Well, do you know what the current thinking is for that?
You could only build to withstand. The same technology has already been tested and proven on the space station itself.
Right.
So that approach, and they will be able to get away with more sturdy construction on the moon because they have less consideration. They don't have to worry too much about what is in the weight or mass in orbit because they're on the surface of the moon. So they can build sturdier structures to withstand those sorts of impacts.
Plus, you have raw materials that you can use, so you can, you know, I'm sure we could use the moon dust to make some kind of cement or something.
Yep. Point. I'm sure in some lab somewhere all of this is already being tested.
I'm sure.
Yeah. I don't think there's any deterring setting up a moon base now. It's already on the books and it will happen.
One of the things that is interesting about the dust on the moon that was discovered through the moon landings is it's extremely abrasive because there's no weathering on the surface of the moon. The dust has very sharp edges and it's very abrasive, and that certainly caused them some problems with wear and tear on their equipment when they were on the moon. That's just something to keep in the back of your mind. So that's something that you know I don't know if they anticipated it or not, but they discovered, and they also said that it had an interesting smell. Remember I was talking about that as well.
Sulfurous. But it's like that is a wicked combination of being very fine grained, but also very abrasive, which means it can get into the gears. They had lots of challenges in getting a proper design for the rover, and it did show a lot of wear and tear, even for the short duration that they did drive the lunar rovers across.
Yeah, still have an meeting. Look, the moon.
A lot of wear and tear.
On that note, David, is the same is not necessarily true of Mars, though. In the sense that because there's an atmosphere, there is weathering on Mars.
That's right.
It's less of a problem.
We heard the wind, the sound of the wind.
Yeah.
Recorded with the Perseverance rover. It's so cool.
Yeah.
But yeah, the particles on Mars, yeah, they would have had their wearing down just by
being blown in.
Wind erosion.
Yeah.
Yeah. So you shouldn't have that much of a challenge.
Oh yeah, hi, good night, everyone. Sorry to be a late entrant, right? And I obviously missed a lot at the beginning, but that's okay. Following on from what Max had asked, I wonder if maybe he was saying, or I'll say, what would this moon, like the same place that we're looking at now, the same shot we're looking at now, what would that have looked like, you think? Maybe 100 years ago, 1,000 years ago, maybe 10,000 years ago? And what would you think it might look like, in another 1,000 years? In terms of the craters, in terms of the cratering, would we see, how would those craters have changed over that time span? What do you think?
Well, there's evidence that the moon, well, we know for sure that in the, let's call it quote unquote early years, after the formation of the moon, there was a whole lot more debris in the solar system, a whole lot more particles and meteors, asteroids that would have had and created far larger impact craters that we're seeing on the moon. And what happened is that quite a few of those craters, when they impacted before the moon had properly solidified, so to speak, the impact craters would have caused the welling up of
what are you gonna ask
magma
for?
from beneath the surface and created those smooth plains. We call them mirrors, sea of tranquility, sea of serenity, etc.
You should be going
really
to sleep.
smooth areas here.
So please go on.
They're basically filled in much larger craters that would have been created from much more heavy impacts on the surface. So that's the thing. Whereas there was no erosion, because the interior of the moon was still a little more molten, you do have a lot of evidence, a lot of cases when you look around the surface of the moon where those impact craters, they were just covered over with magma flows. So it's to say that it was, what we're seeing now is what is left. The moon has cooled, solidified. The impacts that happen now will probably be around for a lot longer, but because the impacts now aren't a result of much larger meteors, much larger asteroids, much larger objects colliding with the moon. It's going to be many small craters rather than the really big ones you saw in the past. So it has its own beauty in and of itself. It's a fossil record of a lot more activity that was happening back then in our solar system.
There's a question here. Is there wind on the moon?
No, there's wind on the moon. Mind you, it does have a very, very tenuous ionized atmosphere, the atmosphere of ions that are kicked up by solar wind when it impacts on the surface. So during the day, the lit areas of the moon, you get this very fine, very thin layer of ionized particles hovering just above the surface. On the dark side of the moon, in the absence of that solar wind, those particles then descend back onto the surface. So there's no, it's very low, right? If there's any atmosphere at all on the dark side, it's lower than it's appreciably, or can be appreciably measured. Having said that, too, I mean, part of what on a different night with a different star might have been able to measure. Remember the occultation, you would have seen the star go right behind the limb of the moon. So a star has a very unique spectrum. Every star has a unique spectrum. In a situation like this, you would have had that very thin layer of ionized particles hovering just above the surface of the moon. So when the star passed behind that, what we would have seen through a spectrograph is the spectrum of the star would have changed, because the light coming from the star would be passing through that now very thin layer of ionized particles. So that was an early way that they detected that there was actually something there. We can't call it an atmosphere in the strictest sense, but there was a layer of particles that was altering the light from distant objects as it passed very, very close to the moon. So, yeah, but ionized particles, no oxygen, no air as we know it. Without any air, you have no chance of wind.
How thick is that layer of ionization, David?
Oh,
Any idea?
um, no, actually, what they do say is that it's very, very rarefied, such that think of it, it's a lot like get an estimate as to how far. No, actually, no, I don't say that. Just like the sun has its outer atmosphere, so to speak, where the solar wind then streams particles away from the surface. In the sense that there's no boundary, like how we have, even our own Earth, it has an exosphere, such that the atmosphere just gradually thins out further you get from Earth. The same thing happens on the moon, except it starts really, really thin anyway, very rarefied. It's like one molecule per square meter or something, one ionized particle per square meter of space. So, it's not to say that you can appreciably measure it anyway because it's so rarefied. Yeah. It just thins out into nothingness at some point far enough away from the surface.
I would think that if the solar wind, which increases and decreases, you could have a point where it increases and that covering may actually expand.
Yes. Well, actually, studies now into the effect of our own magnetosphere, how it can protect the surface of the moon from the effects of the solar wind. There's actually studies that are currently ongoing. Very interesting stuff. That are, well, I guess it makes sense when you really think about it, but they weren't before now with the lunar orbiters in place. They weren't able to appreciably measure those sorts of effects, how these solar particles actually do behave in our magnetosphere and how it's almost like wrapping around the moon, because they say that solar particles can in the end land on that far side of the moon, even though the moon would normally have been shielded. But in that state, it is not, the solar particles do not have it's not an ablative effect, because it's actually been slowed by our magnetosphere, and then it ends up depositing material on the far side of the moon. And you'd appreciate that material, quote unquote, coming from the sun. A lot of it is hydrogen ions. So they actually found got higher deposits of hydrogen elements, or isotopes of hydrogen, which would be useful when we start setting up our moon bases, because hydrogen, not only is it a useful fuel, combine it with oxygen, you get water. So it's a lot, so you can see now why you're getting all of this information, because it's currently investigating all possibilities of setting up moon bases. So any sort of elements that are there that can be harvested for setting up moon bases, yeah, all the investigations are going on now, and you're getting all of this useful insight.
So David, if I'm going to interrupt you here, I'm looking at this image, at this thing that's about to start to go off the screen, kind of just above halfway, and it looks like that's about to go off the screen.
Oh, but okay, here?
Down a bit. Right there, yeah.
Oh,
so that's
a chain.
A series of
Clavius, yeah.
Of
the crater Clavius. Yeah. So the whole crater is called Clavius, and it's Clavius and then Clavius A, B, C, D. And yeah, we do have cases where they're very active. Or back when, yes, the impacts were far more active and far more frequent, you'd have had a chain of particles, chain of meteors, chain of what have you, impacting on the surface of planets. Moon is like I said, it's that fossil record, because most other planets, well, you think about it, Venus, the eroded away Earth, you know, wind erosion, etc. Mars, same thing. But the moon is a very accurate record of those sorts of impacts.
It looked kind of almost like if they were constructed.
Yeah, you know. But there are other examples on the moon, and you just have to, well, actually, they will become more apparent as the phases change. Like right now, if at yesterday you would have seen this, this would have been far clearer. Right now, the Terminator has advanced further towards the west. Yesterday, it would have been right around here. So that chain of magnitude is still very clear. And that is true for other similar locations on the moon where similar impacts would have happened. It's cool stuff. Is that anything? It's just so much to see. It's so much to see. It's really to take time and explore what you can see, because even basic observations, there's so much that you can see and appreciate. Yeah.
David, I noticed several of the craters
Mhm.
seem to have mounds in the center.
Yeah. Mhm.
I mean, more than one, you know.
Oh yeah. Most, okay,
I
the
mean,
vast
some have
majority.
craters within craters, but there are some of these larger craters that have mounds in the center.
Yeah.
I'm seeing like 3 right now.
Oh, there are many more. Yeah. Yep. Let me just scoot you back over here, because all of these, oh, because tomorrow you'll probably see these two a little better. But yeah, they do have peaks in the middle. Basically, when the meteor or whatever object struck the moon, the force of the meteor would have caused a rebound. So you get that initial impact. The material at the very center of the crater is compressed initially. Material would have been ejected out. But, this is Copernicus. Right, material would have been ejected out. You see these big rays here. But then you imagine the center would have been compressed in the impact, but then it rebounds back out, and it causes that central peak right there. And all of these would have formed at a time when, yeah, basically, well, not so much when it was in that semi-molten phase, though, because normally, say normally, because there are actually several cases where impacts would have been filled in afterwards by lava flow. Did not happen with these. So they got a sense that this actually happened after that phase in the moon's life. But yeah, that is a common feature. And it's purely mechanics, so to speak, the mechanics of the impact itself that would
Okay.
have caused that welling up in the middle.
Do we know if the moon has a core that may be of a different temperature? Or
It's
not?
a core, but it's dead in the dirt. So certainly not molten. If it was, then you would have had a magnetic field. The moon has no magnetic field. But based on what we understand to have been the process by which the moon was formed, it's largely comprised of similar elements, similar materials as the Earth itself. That actually is, I don't want to say that the theory came before the investigation, but I think the current theory in terms of how the moon was formed, what they know about the moon now, what we know about the moon now, further supports that theory. That was a result of an impact between some other body and the Earth, caused material to be ejected out and gradually coalesced, formed the moon. I said also that it's mostly the same material as the Earth, because there is evidence of other material that had to have come from another body. So they know, chances are that is that material from that other body that collided with the Earth. So, fascinating stuff. And interesting to, if there was some other way that we would have been able to, hinting more than once during this presentation, that the moon does capture. It's like a fossil record of all that happened before. It's just to go back that one step further into the actual formation of the moon, so you would have been able to see, I think a whole lot more questions would have been answered about how the Earth-Moon system was formed. It is right now. It is a theory that is supported by the evidence. It's always best to have that confirmation. Say for sure this is what happened. Appreciate some of the forces involved here when you see an impact crater that ejected material that spans from here, this crater Copernicus, it goes all the way, and it keeps going. Sorry. Yeah. Here. And then there are other impact craters that expel materials similar distances. It's a lot of force, a lot of energy released. Think about those much larger craters that happened in the past, result of far more heavy impacts. You can just barely make out the crater rims that still exist. I'd shared a photo of the moon, the color photo of the moon. This crater here is actually a striking blue color. It's quite interesting. Evidence of a whole lot of all different elements in the surface. So the blue areas are iron poor, whereas the reddish areas are iron rich. But this being a monochrome camera, well, I'll probably try to do some these close-up color images so you can see. I really appreciate the variation, the color and the surface of the moon.
We're having a bunch of people are hitting their bedtimes.
Yeah. I should too.
But, I thought this was extremely interesting. Certainly generated lots of questions and food for thought.
Definitely. So, well, we can have our.
Thomas, was it recorded?
Yeah.
Okay, great.
It's being recorded. So
yeah, thanks.
At some point that will get disseminated.
Yeah, that's okay.
Cool.
Yeah. So yeah, we have our postmortem, like I was hinting at earlier. Yeah, we can have the presentations. If it's at all possible, just pick a target that is currently visible in the sky, and we have a viewing session. And it's the best we can do in this virtual approach. You see that if we weren't in these COVID times, we probably would have just progressed from the auditorium up to the dome and taken a viewing session through the main scope. This is probably the best approximation we can get to that virtual world. All right, so yeah, I think this actually went very well.
Yeah, but of course the question is, how do you monetize it?
Well, right now, I can only tell you that we that's almost, I wouldn't say it is a primary concern right now, not right now, because the reality is that we as society still must try to fulfill the mandate of sharing whatever information about astronomy with the wider public. If we along the way can accept donations in support of our efforts, then we're always willing to do so. But even in the absence of that, however we can try to strive on and fulfill our mandate, we'll do that. We'll do.
We're not hearing you too clearly, David, at all.
Sorry, yeah, still in the wind, still outside. I really can't afford to here right now leave the scope because there's still the threat of rain, right? But what I was saying is that we'll still try to do our best, even in the absence of being able to monetize these efforts, to fulfill the mandate of sharing the knowledge of astronomy with the society at large, right? If along the way we develop the means by which we can monetize it, then yeah, we'll proceed along that path. But you know, the key thing is to make sure that we share astronomy with the Barbadian public and even beyond the borders of our country, because that's what we do as an astronomical society. That's what we'll forever strive to do. Things, the COVID situation will not last forever, and we will get back to doing, actually we'll probably be doing elements of what we've learned under these circumstances in addition to what we were doing in the past. So I think we're perhaps better for this whole COVID experience. So I think we will build on this newfound knowledge and approaches and come out stronger as a result.
And David, I think once we can generate the interest from the wider public, when the COVID times, whenever the COVID does come to an end, and we can get back out there, then we should be able to increase the membership. And I also believe that the online way of doing things now can probably reach a much wider audience.
Certainly.
That could at the observatory. But even when we've had some of the nights, the logistics of managing large numbers and keeping everyone satisfied is a little challenging. Whereas with online, you can have 1,000 people all viewing the same thing at the same time, which could never happen at the observatory either. So these are one thing, the thing that we should take advantage of now, if we can reach as many people as we can using the online forum, then and generate that interest. When we can go back and view the scope, we should have more persons interested. That's just my view.
100% correct, 100%. And add to this, because imagine the solar eclipse was probably a classic example. Now that we've learned how to stream our views through the telescopes, then when you have multiple views of an event, you would less be, well, unless it's a complete cloud over, completely clouded out island-wide, you have that opportunity to share an event that's happening in real time from different locations and provide adequate coverage of what is happening up there. It's techniques like this that will stay with us. We'll build on them, and yeah, because like I said, we have that much wider audience that we can provide content to, and we can do so a little more reliably now with the virtual medium, because you have multiple sources providing the same content, and become more resilient in that way. I'm
I
actually
think
the
we're
less
also gonna have to push a little harder into the social media aspect. If especially those video or photography based social media where we can post short clips of different phenomena, different celestial bodies, whatever, and just get that out there as well. Not that we have not the time, but know that more persons are using social media, to me, more than ever, because you really can't physically be out there. So I think that was a pretty good opportunity for us to really spread the word of the observatory, because people can't actually get out, so they're doing more things inside. And if we can get them hooked using Instagram or Facebook or maybe even Twitter to an extent, I think we can really increase the membership that way, or at least the interest.
And thanks, Orville. It, the board has certainly been thinking along similar lines. So, I mean, it's for us, it's a learning curve as well. And we are going up the learning curve. We are using more and more social media to get the word out there. Again, we're learning, but certainly it's very much in the headlights for the current board to head in that direction, because the world is not going to be the same after this. So agree with you completely. So I think when COVID is over, you will probably see a hybrid approach, between having presentations at the HBO and online. You'll see a combination of both, and a mixture of both at the same time, and things of that nature.
Yeah, I think a blended approach would work well, because it's not going to be every Friday night that you're going to be able to get out and go to the observatory. But if you can still take part in it, then you still benefit.
Yeah.
So I think a blended approach would be a really good idea, to be honest.
Certainly, that is how we're thinking about the future. So, agreed completely. Does anyone else have any questions or observations? This is actually being recorded, so at some point in the near future, I believe we may make this available. And when that happens, you will be informed. But David, I was going to suggest that we could probably think about wrapping this up, because the hour is
yes.
a bit later.
All right. Well,
We've had some folks leave us. So,
yeah. All right. Well, I just want to thank everyone for coming out and being a part of this event. We'll be hosting many other events in the future. In fact, at any given opportunity, we have a celestial event for certain that we can provide in the live coverage and share with you that way. We'll definitely have an event. We'll be having more outreach events in general. But you can appreciate the format that we offer this evening. We'll be following, those future events will be following a very similar format where possible. So just stay tuned and follow us on our Facebook page. And those of you who are members of the WhatsApp chat, you will always be in touch and in tune with what is happening as well. So with that, I just want to thank you all again and wish everyone a safe, pleasant night, and take care until our next event.
Okay, thank you, David, and good night, everyone. Great. Okay.
Bye.
Bye, Philip.
You too.
David, as you are the host, you can end the meeting.
All right. See you all. Take care. Be in touch.
Good night. Bye.
Good night. Bye-bye.